on advancement in science and technology. Our today's speaker, Dr. J. Muralidharan, is a professor of geology in Arba Minch University, Ethiopia, and Sir has vast experience in teaching, curriculum development, research, and also for the PhD mentorship and guidance. So, before wasting much more time, I invite Dr. J. Muralidharan sir for his session on space technology for geological applications. Please, sir.
Yes, sir. Is my screen is visible to you, sir?
Yes, sir. Screen is visible.
Okay, sir. Okay, sir. Okay, thank you very much. Good afternoon to everyone.
Good afternoon, sir.
Thank you very much. Thank you very much to Phaltan Education Society, College of Engineering, to giving me this opportunity to deliver the speak in that international conference on advancement in science and technology. I'm going to deliver my keynote speak on space technology for geological applications. So you know, the remote sensing plays an important role in the different aspects of natural resources, the disasters, and the environmental applications. Here we have the different Earth features. Like we have the multispectral data, hyperspectral instruments, and the SAR, LIDAR. These are all the LIDAR, drone, and all some latest technology which is helpful to identify the Earth features. So these instruments are these sensors are helpful in geological mapping, land use, land cover classification, and monitoring environmental changes like deforestation and land degradation and all. So, in particularly, this space technology such as remote sensing is highly valuable tool in assessment of water, surface and groundwater, mineral resources, and hydrocarbon resources such as oil and gas resources. So we have the different instruments to map the these earth features in order to identify these natural resources. Apart from these resources, it is also highly useful in the disaster monitoring and management. Particularly, we can do the real-time monitoring the natural disasters like earthquakes, volcanic eruption, landslide, and flood. So this technology will helpful for assessing the pre-damage and during the damage and as well as the post-damage assessment in the disaster. So it have the rich of sensors to assess the disasters, as well as it is highly helpful in the studying the landform. So the landform in the sense there are different landform which is favor and which is non-favor for different geological resources as well as the disasters. So by using the LIDAR and advanced digital elevation model, we can map these landforms. Then it is also one of the major tool in the water resource management. As you know, we want to assess the freshwater resource in it is quantity and quality, as well as we want to map the groundwater quality and quantity. So for this kind of studies and projects, we can use this remote sensing data to map these controlling parameters and find out these water resources. So here, just I want to introduce some fundamental concepts of remote sensing before going into the different applications of this technology. So here we have the platform and sensors. So majority of remote sensing data comes from the satellite. We call sun synchronized satellite. So mostly we get our remote sensing data, different optical, hyperspectral, and SAR data, synthetic aperture radar data we get from the satellite. Apart from the satellite, there are aircraft, balloon and all is there. So there are different sensors are there, like Landsat sensor, thematic sensor, NR thematic sensors. Then recently we have the Landsat OLI sensor. Then there are sentinel sensors. There are a lot of sensors are there. These sensors are helpful to map the different earth features. This is the overall remote sensing process. This is all about the passive remote sensing. Here the major source is the energy source is the sun. Sun illuminating the earth by in the name of electromagnetic radiation. There are a lot of spectrum or the electromagnetic spectrum. Before it reaches to the earth surface, it will interact with the atmosphere, and there is a energy losses will be there in the name of energy dispersion and scattering and all. Absorption, scattering and all will be there at the atmospheric level. Particularly, this will be affected by the optical remote sensing sensors because the atmosphere have the different matter. This is solid,
Hello, sir.
liquid.
Hello, sir.
Yes, sir.
Slide is not changing.
Not changing, sir. So is it visible, sir? Hello.
Yes, now it's
Yes, visible, sir.
Yes, sir. Yes, sir. Maybe just please tell me, sir, because maybe internet problem. Sometimes slide is not changing there. Just inform me whenever it is not changing. So this is the overall remote sensing process. Once the energy is interacted with the earth surface, it reaches to the onboard sensor, which is kept on the satellite. Then it will there are different sensors will be there, like multispectrum, hyperspectrum, and microwave sensors will be on board on the platform. So it captures it is own range of spectrum, and it transmits the energy to the signals to the ground station. Then the data processing unit will process, and we get the different forms of satellite imageries. So this is all about remote sensing process. This is a passive remote sensing system, particularly optical as well as hyperspectral remote sensing. It operates in the passive remote sensing system. Here the sun is the energy source. So it illuminate and radiate and the earth surface, and the returning energy will be captured by the onboard satellite. This is all about passive remote sensing, and this is active remote sensing, particularly microwave portion of the energy. We use this active remote sensing system. Here the sensor itself, it sends the energy, and it detect the earth object. So this is particularly the microwave portion. We use this active remote sensing system. This optical remote sensing system will not work during the cloudy season, particularly in the monsoon period. You cannot see the earth object in the multispectral remote sensing data, because the entire spectrum will be completely dispersed by the cloud in the atmosphere. So we cannot assess the flood, particularly during the heavy rainfall. There is a flood problem is there, but we cannot see the terrain during flood using this multispectrum remote sensing data. To overcome this, we have the microwave data. This is 1 meter wavelength data is there. So this data, these sensors can easily penetrate the cloud. The energy cannot be lost in the cloud, so it can easily penetrate the cloud, and it can detect the earth object. So So for the particularly in the flood-like disasters, we use this SAR data, synthetic aperture radar data, to see the damage because of flood. And this is the another remote sensing we call hyperspectral remote sensing. Here we have the many number of small interval bands will be there. So this will helpful particularly in the mineral mapping, then soil mapping and all. We use this hyperspectral data. So particularly we can divide the entire remote sensing into three categories like multispectrum and microwave, then this hyperspectral data. So this is the overall atmospheric windows where we can get our data. So if you see between 0.4 to 0.7 is visible spectrum. This is our naked eye spectrum also. Then there is a reflective infrared, thermal and microwave remote sensing. So beyond this and above this, the sensors cannot work because most of the energy will be scattered and absorbed by the atmospheric particles. So there are some important resolution we have to consider while selecting the data for our study. So these resolutions, this is we call resolutions. So the resolutions are mainly four types are there. Particularly spatial resolution. The spatial resolution is saying about the size of the pixel. The satellite imageries are made up of pixels. It's a raster format and made up of pixels. If the pixel size is small, then the detail will be high. So depends if you want to do urban mapping, then cadastral mapping, then we have to go for detailed satellite imagery in order to identify the feature in very detailed. So depends upon the need of your study, you can select the spatial resolution data. We have starting from 80 meter to sub-meter level data we have for our different purposes. So here you can find the 10 meter resolution data, 30 meter and 80 meter resolution data. The same area, you can see how it is looking in the different resolution. If you want to see the Earth object very clearly, you have to select the high spatial resolution. That means among the three resolution, 10 meter is the high spatial resolution data. So you can select this data for your detailed study. For your small scale study and all, you can go for medium and high resolution data. Then spectral resolution. So as I told you, there is a panchromatic, multispectrum and hyperspectrum data are there. So depends upon your need of study, you can select the different spectral data. Then temporal, this is we call revisit of satellite. So each and every satellite have their own revisit in the particular space, so particular location. So this is highly helpful for the studying the drought, flood and forest monitoring, forest fire. So wherever the temporal changes are there we can use such kind of data. As I told you, vegetation changes, dynamics, weather changes, forest fire changes, then volcanoes. So these kind of studies, we need the temporal resolution. Then the final one is the radiometric resolution. This is the depth of the pixel. So if this is measured by bit. So each and every data have their own bit. So if the bit number is high, then the pixel, the shade of the gray will be high. So you can easily demarcate the Earth object by using this radiometric resolution. So this is the overall structure of the remote sensing data. For example, I given the Landsat data. Here we have the 7-band multispectrum data starting from blue to mid-infrared. So this is a 7-band. This is we call multispectrum. If the number of bands are high, then we call hyperspectrum, particularly Aster, Hyperion. These are all the data are the hyperspectral data. So this is the overall milestone of the space technology, starting from 1860, 2020. Now we are using drone, lidar. These are all the some advanced technologies we are using in this geological purpose. So just I want to show some direct applications of this remote sensing GIS. So most of the studies are conducted by us here through some research projects and other means. So just I want to show some few applications. We have conducted a lot of studies. Here I want to show the few applications through our publications. So in this one study, we have used the digital elevation model synthetic data to identify the major structures in the main Ethiopian Rift Valley. Here the Rift Valley have the causes for different earth system like volcanic activity, earthquakes, and geothermal activity, and all. It is very active here. Today also it is very active in Ethiopian Rift system. So to assess here the structure means there are fault, fold, there are geological structures are there. So by using the this digital elevation model, we tried to assess the structure in the southern main Ethiopian rift. So this is the rift. In the left image, you can see the main Ethiopian rift starting from the, and still it is going down to the different countries. This is the Ethiopia boundary is shown there. So that rectangle box, we have conducted the study. So by using this digital elevation model and aeromagnetic data, we incorporated both and using different remote sensing, that means image processing techniques. We have identified these structures. And here in the right image, you can see the elevation as well as there are different, the black lines are different structures we have identified. In the another study, here there are volcanic activities also is there. If you see the northern part of the rift system, there are volcanic activities, still active volcanoes are there. So this entire rift valley having the geothermal potential. So just by using the remote sensing data, we tried to see the surface temperature. So you know the surface temperature is changing place to place. So by using, this is one of the key factor, we tried to identify the geothermal potential area. Here mainly we use the optical remote sensing data. We derive the land surface temperature. There are image processing techniques. By using those techniques, we derive the this is the study area. It is also the main Ethiopian rift area. The blue polygons and lines indicating the volcanic landforms. There are existing volcanoes and there are few active volcanoes are there, but many places you can see the geothermal activity here. So by using this satellite imageries, we identify the land surface temperature. Here you can see all the red polygons or red areas have the high temperature. This is a Rift Valley region. So you can find some volcano name also, Cone volcano, Rosette volcano. This is a place name and we have the volcanoes. So by using the remote sensing technique, we identify the geothermal activity also. So this is alternative energy sources. We are trying to still focus on the impact, how geothermal activity are impacting the soil and water quality in the particular region. This is all about structure and geothermal activity in the Rift Valley. And by using this remote sensing technique, we try to map the flood susceptibility in the Blue Nile Basin. This is the catchment. This is near to Lake Tana, where the Blue Nile is originating. So here, this area is highly vulnerable for flood area. This is a floodplain area. So by using the remote sensing, we try to assess the flood proneness in the particular area. In the right map, you can see the point. This is a GPS location. There's a active flood prone areas. So this is the entire catchment. We try to map the flood proneness. So these are all the different flood controlling parameters we mapped using the remote sensing data like slope, elevation, then groundwater depth, land use, land cover. These are all the 9 parameters which is controlling the flood in the particular area. So by using this space technological data, we map these data set first, and after that there are statistical models like analytic hierarchy process and frequency ratio. There are bivariate, multivariate statistical techniques. We applied these techniques over these derived controlling parameters. We identify the flood-prone area through the develop the 4 models. These are the 4 maps show the 4 different models. So now we may have which model is correct to do the further study or to implement the strategy to control the flood. So there is a technique, statistical technique. So we can directly compare the existing model as well as the actual flooded data. This is called the area under curve method. By using this predictive curve and success rate curve, among the 4 models, we identify that the frequency ratio is a suitable model in the particular area. So this is one application of remote sensing GIS in the flood study. Then in the another study we conducted here in the Rift Valley. To here in the entire Ethiopia, is the major problem. The African continent, Ethiopia have the number 1 in the soil loss. So there are several studies they keep on conducting to identify the to control and identify the soil erosion in Ethiopia. So we also participated on project and our findings were reported here. So we tried here using the different drainage morphometric analysis. These drainages are derived by using the SAR data, data. Then there are a processing technique. After processing, we calculated these aerial and shape drainage morphometric parameters. This is their parameters and their formulas and calculative methods are given here. So we know there are some parameters are directly related with soil erosion, like drainage frequency, density, bifurcation ratio. These are all some parameters have the direct contribution to the soil erosion. And there are different parameters. There are different parameters such as length of overland flow, and other parameters have the reverse relationship with soil erosions. So there is a statistical method, weighted sum approach. Using those approach, we identify these areas are particularly what is the 3 have the very high proneness to the soil erosion. This is a highland. Here the elevation is around 3000 meter and a lot of gully erosions are there. So this has been proven by our drainage morphometric analysis. So this is another study we have conducted here. Then this is also another flood susceptibility study we conducted in the Blue Nile River Basin. Particularly in the northern Ethiopia, many parts are suffering the flood problem. So we conducted the study and by using the drainage morphometric analysis, this is the lake is the origin lake for Blue Nile, Lake Tana. You can see in the blue color. Lake Tana is the origin point of Blue Nile River. So the upper catchment always facing the flood problem. So we conducted this study. We identified the flood prone areas in the particular catchment. So these are all the different applications, remote sensing applications we applied, and we conducted the different studies. In continuation that, in the Rift Valley region, again we conducted another study, estimation, quantification of soil erosion by using the Russell model. Using the remote sensing GIS and Russell model, we quantified the soil erosion. Here most of the data are input data are the derived from the remote sensing data, particularly slope, then land use, land cover. These data sets have been derived from the remote sensing data, and there is a standard formulas are there. Applying those formulas, these are all the input factors like slope length, land use, land cover, practice factor, then soil factor. These are all the different factors are there. So we derive the many of the factors by using the remote sensing data, and Finally, we quantify the soil loss. It is between 0 to greater than 128 tons per hectare per year. So this is another study we conducted, particularly in the soil resources. Then coming to the disaster, we have conducted the landslide assessment also by using the geospatial tools, particularly remote sensing and statistical approach. The study was conducted again in the northern Ethiopia in the Blue Nile River Basin. So these are all the different data sets we use as a input, particularly slope, aspect, elevation, curvature. There are many landslide controlling parameters are there. And we developed the two statistical models like frequency ratio method and information value method. So this is the two methods showing the landslide vulnerable areas in the particular catchment. As far as the water resources concerned, again we have the many projects. So through those projects, we have published papers. Just I'm showing as a case study here. One of the paper, it is a very drought-prone area in the southern Ethiopia. Here we use some statistical models. These are all the input data like linear and drainage, soil geology, land use, land cover, drainage, and using those data sets, we adapted here the table shows the different data sets and their sources. We adapted the bivariate statistical methods, and we developed the groundwater potential zones. This is one of the very drought-prone area. You might have seen the drought in paper and news and all. This is one of the area, very severe drought-prone hit area. And another study, this is also conducted in India. Here we use this remote sensing data and geophysical data. We integrated the remote sensing and geophysical data in order to identify the groundwater potential zones. These are all the input data. Here we incorporated additionally the remote sensing data. We incorporated this resistivity data sets also. So we incorporated those data sets and we identified the groundwater potential zones. So this is the output of that study. And recently also we conducted the one study, assess the recharge potential. Here also remote sensing plays a major role in assess the groundwater recharge potential zone. There are different model sets are there. In this study we have selected the wet sparse model. This is a well-known model. So we selected that water balance distributed model. So there are many input parameters we have to give, like evapotranspiration, then wind speed, temperature, rainfall, water level. There are several input parameters we have to give. There is a standard formulas are there. Once you give this input and apply the formula, we will get the surface runoff, how much runoff is there in the particular catchment, and what is the how much amount of water is recharging. So surface runoff, evapotranspiration, and recharge can be quantified. The previous studies we just map the spatially the potentiality as well as the hazard zones. But using this model, we can quantify the surface water, how much surface runoff is there and how much water is percolating to the ground. So it is highly useful for managing the surface and groundwater, particularly for irrigation and drinking and other purposes. These kind of studies are highly useful. So this is the output, like surface runoff calculated for yearly and season wise also, summer, winter, how much runoff is there. And this is the overall recharge, how much recharge is and where is the recharge potential zones are there. So by using this output, we can suggest we can recommend the boreholes and other groundwater development activities in this particular area. So this is all about the studies we conducted for water resources, soil resources, and disaster, particularly flood disasters, landslide disasters. So these are all the studies we have conducted here. Apart from that, we study some land use land cover dynamics also. This is also because nowadays the climate change is very drastic, and it is there is a rainfall pattern also changing, and the temperature is rising. So we want to know the changes on the climate change and related with your this biophysical resources. So for that we have carried out some land use land cover dynamics also. This study also conducted around in Rift Valley region. This is the area we have conducted our study. Here mainly we use the different remote sensing indices like normalized different vegetation index, building index, barren land index, and water index. There are many remote sensing indices are there. We have selected a few indices for our study, and we have taken the data set between some 2013-20. So we have taken some temporal data, and we derive the land surface temperature. So we want to know, because the land use land cover is changing, many of the forest area is getting deforested because of some agriculture activity, poisoning activity, and firewood purpose. The deforestation is very intensive here. So through land surface temperature, we can correlate with the forest area and how the temperature is increasing. So when we cut the tree, automatically the area will become a barren land, and the land surface temperature will be high compared to previous forest area. So we keeping this concept in mind, and we develop these models. We derive the land surface temperature, and if you see this image, the temperature is increased between 2013, and we taken the 2020 image also. Then when we calculated the land surface temperature, it shows a difference, and the temperature also increased. So we want to confirm by means land use land cover dynamics. So we done the land use land cover classification, and we compare this result with the land use this land surface temperature also. So further we developed the NDVA. NDVA is one of the indicator to identify the healthy vegetated area, particularly forest area, as well as by using this NDVA index, you can easily demarcate the water body and barren land and settlement. We can easily identify, and we can easily demarcate. This is one of the accurate method to do the land use land cover mapping. Here the indices value between -1 to +1. So whatever indices you are considering, if it is near to +1, it is indicating the richness of the particular object. Suppose if we are taking the NDVA, normalized difference vegetation index, if your values are closer to +1, then it is indicating the healthy vegetated area. If it is closer to -1, it is indicating the water body. Here you can see the large water body are there. You see in the upper map, the top map, there is a large water body. This we call Lake Abaya. This is the second largest lake in Ethiopia. The first largest lake is Lake Tana. This is the second largest lake in Ethiopia. So this the left side is the rift margin. It is goes up to 3,000 meter height. The lakes are situated 1,200 meter height. Yes. Hello. Sir, is there any interruption? Your voice is not audible.
No, sir. No, sir. No, sir. Carry on. Please.
Okay, I hear some voice. That's why I stopped. If you see the top map, the Lake Abaya, there is another lake. The down one is we call Lake Chamo. There is a hill in between two lakes. Very beautiful geological formations are here. So this, the left side, you can see the high mountains. This up to 4,000, 3,500 to 4,000 meter heights are there. The slopes also very high. So it causes for severe soil erosion, and there is a lot of landslide, intensive landslides also is there. So we give more focus in this area, particularly water resource studies, soil resources, and disaster studies. We keep on doing the studies here. So this study, particularly this study shows this normalized difference water index. So this study result shows there is a intensive land use land cover changes in this area. Particularly the forest area is changing into agriculture for pasture as well as settlement. So this causes severe environmental degradation in the lower lake part. Particularly these two lakes have the different ecosystem. So because of this, a lot of landslide as well as soil erosion, there are large rivers are there, perennial rivers are there in this area. So it brings a lot of sediment and it causes a siltation problem in this particular area. So the another land use land cover study also we have conducted in the Ethiopia's capital, Addis Ababa city. Here also we have conducted this study because the urbanities keep on expanding. So we wanted to know how much expansion is there in the temporal scale. So for that we have taken the 2000 satellite image and 2011 and 10 years interval we have taken the images, and we identify the different remote sensing indices also. Be compared. This is the chart plot is showing the NDVI is keep on decreasing. The top one is 2001 NDVI. The bottom one is 2021 NDVI, normalized different vegetation index. So it is clearly indicating this value is derived from the pixels, remote sensing pixels, the satellite data pixels. So this chart shows the NDVI is, that means the healthy vegetation area is keep on reducing. You can see the peak is becoming flat. It is indicating they remove the forest area and they keep on construct the buildings. So it is confirmed by the right graphs. This is nothing but NDVI graph, normalized difference build-up index graph. It is indicating, if you see the 2001, how the graph is very broad. Then if you see the recent one, 2021 graph, you see it is closer to +1 value. So it is indicating the urbanities keep on expanding. The values in the y-axis also, the values are keep on increasing. So by using this remote sensing data, we can do the environmental studies impact assessment also. So this is a few studies I shown us here, or one case studies I shown as an example, how it is useful for environmental impact assessment. Then we can do the, using the remote sensing data, we can do the solid waste, we can do and select the solid waste disposal site selection, because everywhere the urban and the settlements are keep on increasing. We want to identify the suitable solid waste disposal site in order to avoid the surface and the groundwater soil pollution. We wanted to identify the suitable solid waste disposal as well as liquid waste disposal site also. In this study, we have undertaken taken the solid waste disposal site selection by using the remote sensing and GIS data. So here there are many parameters is involving to select the suitable sites for solid waste disposal site, or you can say landfill site. So in this study, we have considered the 13 parameters, starting from drainage up to wind direction. So most of the data sets has been extracted from the remote sensing data. So slope, elevation, aspect. Aspect is nothing but to measure the wind direction. We use the aspect. Then precipitation. If there is high rainfall, there is a chance for high erosion and it causes for surface water pollution. So we consider these parameters and we map these important solid waste disposal site selection parameters, and we mapped also. And finally, we identify these areas are highly suitable areas for solid waste disposal side. So government can take initiative to do the further investigation here, like geotechnical studies and all they can do, and they can confirm the soil and the rock quality to go for further installation of solid waste disposal site. So I wanted to make the concluding remarks. So by using this space technology, particularly in the geological applications, in the geological studies, we have n number of applications, starting from water resource assessment, surface and groundwater resource assessment, and different natural resource assessment, and disaster assessment and all we can do. So now we have still space to go forward by using the drone technology, then advanced machine learning, and nowadays there is a machine learning techniques easily identify and extract the landslide sites and all. So now the technology and the coding is becoming very strong, and using those technologies still we can go forward, and we have a lot of space to work in this area by using the remote sensing GIS technology. Thank you for once again, thank you for giving me this great opportunity.
Hello, sir.
Yes, sir.
Hello. Am I audible?
Yes, sir. Yes, sir.
Okay. Thank you, sir. Your efforts have been shown through your presentation. The pictorial and graphical presentation has made all of us enjoyable this particular session, and the efforts you have taken are really appreciable, because you have given information about satellite, and that Ethiopia, we really come to know about Ethiopia, how the things are going on in the Ethiopia through your presentation. I once again thank you. Thank you for your presentation and lovely talk through this session.
Thank you very much for this great opportunity, sir. Thank you.